Professor David Carver from the Department of Engineering in Cambridge. He has a group that does some very difficult science, which involves trying to make the best samples in the world and then trying to understand the superconductivity and their applications. So I shall leave it at that and leave David to pick up. Thank you very much.
Thanks, David. So it's a pleasure to be here. So it's nice to get away from Cambridge for a day and to talk about the work here. So David and I have known each other for a long time. And, so what I want to talk about really is bulk superconductivity. And bulk superconductivity is essentially large and localized. So we make big samples with the best possible properties, and any energy or properties that we're interested in are very much locally oriented. And we're going to be talking mainly about melt processing, which is a process developed over the last 50 years to make rare earth barium peroxide superconductors. So here's the rest of my group. She makes the materials. Harry Babu, who's done a lot of characterization. John Burrell, Sandeep Patak, who's a student, and the students on the project. Tony Dennis, who's our technician. And we speak to Tony when we don't know who else to speak to, so we speak to him quite a lot. And then Archie Campbell, who's been around forever, and most of you may have heard of. So here's an outline of what I'm going to talk about. There's quite a background, there's quite a story to this, and I'll try and put it in context for you. I'm going to talk mainly about recent developments that are key to making good materials, and I think fundamental to how we're going to apply them. I'm going to tell you about how the materials behave, how they perform when we've made them, and then I'll kind of wrap up at the end. I guess the first thing I wanted to say is that in any career there's got to be a huge slice of luck, and I was at the right place at the right time. I got my PhD in '86, I worked for Plessy, in '87 high temperature superconductors was discovered, and they wanted somebody who had a PhD in physics who knew a bit of materials. They narrowed it down to me or the company CAT, and I think on a vote I got it by a short hair. And that one single event transformed what I was going to do for the rest of my career. So I think I used all my luck up in that one particular event. So right time, the right place often makes a big difference. Okay, so here's the introduction. So we have different types of superconductors, and I'm going to be talking about type 2. So type 2 are the ones that we apply practically. And there may be some niche applications for type 1 materials, but they operate really as diamagnets, low fields, and very, very few applications. So we're going to be looking at type 2 superconductors. They operate at high currents and at high fields. Just to give you an idea of progress, this was published in 1992 by a Japanese group, and obviously it's a goldfish. And the goldfish and the jar and the permanent magnet it sits on have a mass of 2 kilograms. And here's a bulk superconductor, and we've got this very nice stable levitation of the goldfish above this bulk magnet. So the whole arrangement has a mass of 2 kilograms. And then 4 years later, the same group produced this. This guy's called Tosonomi. He was the 1996 sumo wrestling champion. And he's on a levitated platform. There's a gap of 2 centimeters. Here we have an array of bulk superconductors. This whole arrangement has a mass of 200 kilograms. So this actually was filmed at the ISS meeting in Sapporo in 1996. And I kind of spoke to this guy, and he told me that the Japanese make the best superconductors in the world. And I wasn't going to argue with him. Another interesting but completely useless fact is that subsequent to this, a Japanese couple paid $7,000 US to be married on this levitating platform. And some would say that's the first commercial application of hydrogen. So if any of you feel like taking the plunge, we now have our own levitated platform, and we'll do it for less than $7,000. Okay, so why are these bulk materials so potentially important? Well, it's fairly straightforward. A, we have to cool them. 77 Kelvin is a convenient temperature. It's the boiling point of liquid nitrogen, which is freely accessible. And given the world helium crisis is increasingly significant. But they're potentially able to trap very large magnetic fields. These fields ultimately will be compared with what you can achieve using a permanent magnet. And And interestingly, the best permanent magnet field you can get is a bit less than 1.8 Tesla. And if you take iron in the form of a long, thin rod, and you magnetize it along its length, you can generate possibly 1.5, 1.7 Tesla. And that's how the Victorians used to make their magnets. But it's limited by the number of unpaired spins per site, 2.2 in iron, and there's nothing you can do about it in terms of processing. So this is an absolute limit. Unless somebody finds a new material, and it's very unclear to me where that may come from, then these are the fields you're competing with. The second point to make is that if you have two permanent magnets, a north pole against a north pole, that repulsion or that interaction is intrinsically unstable. In fact, if you leave a north pole being levitated by a north pole, the top one will flip over and north-south will attract and minimise the energy of the system. So permanent magnets, not only do they have a limited maximum field, they also have this intrinsically unstable interaction with one another. Unless it's north against south, which is not levitation. So where does the subject stand now? Well, I think this is pretty extraordinary, personally. So this is from the same group that levitated Tosonomi, and it shows how the field generated by two samples of high-temperature superconductor can generate a magnetic field. So essentially, you put a Hall probe between two samples, you apply a big field and you remove it, and you look at the output of your Hall probe, and you do that as a function of temperature. And at 29 Kelvin, there's a staggering 17 Tesla magnetic field. It's extraordinary. If you take a neodymium-boron iron magnet, you're lucky to get a Tesla. And the energy density goes as field squared of two magnets repelling one another, or in fact, the energy density is stored in a given magnetic field. So neodymium-boron iron will generate a Tesla. There's a documented incident of a technician in the US getting his finger caught between two neodymium-boron iron magnets coming together, and they took the end of his finger off. That's 1 Tesla. And we talked about iron, and that was a maximum of 1.7 Tesla. So 17 Tesla is 10 times the field of iron, which is 100 times the energy density. And of neodymium-boron iron, it's about 400 times the energy density. So this is a serious amount of energy. And one could argue that you couldn't practically design a field or an application with 17 Tesla. So this is possibly an academic study, but it kind of gives you an impression of the magnitude of fields that could potentially be achieved using these materials. I feel compelled to show this cross-section of the material from the same sample. It looks absolutely horrible. From a purist point of view, and I'm a bit hesitant in the Department of Physics in pointing this out, but it's, in terms of symmetry and long-term order, it's got nothing going for it. However, these microcracks don't carry current in this direction. Current flows out of the board and back in and generates an actual field as we're showing here. So one argument is that if you're applying this and it's going to support a field for a long time, who cares what the microstructure looks like? And the authors claim that these cracks are unfilled with epoxy. There's a big issue between coefficient of thermal expansion of epoxy and ceramic material, so I just wonder how hot this whole thing can stay together. But anyway, this is data which I believe. Okay, so having established the potential, we need to explain why materials can generate high fields. Well, fields always come from current or moving charge, either spins on sites or charge with linear momentum. So essentially, we need to explain where we get large currents from, and they come from flux pinning. So magnetic flux in superconductors exists in the form of long, thin, quantized filaments, Faraday's lines of force, effectively, the kind of lines that 8-year-old children associate with magnetic fields when they sprinkle iron filings on the top of a bar magnet. Of course, field in space is a continuous variable, but you get this notion of fields existing as individual lines. So in superconductors, they really do. And these lines can move through the superconductor, which gives a d phi by dt, and therefore an EMF, and therefore dissipation when current flows. So if you can stop those flux lines moving, you get no induced EMF, therefore no loss. So you get lossless current flow. So the challenge is to put obstacles in the way of these flux lines and stop them moving, and that's flux pinning. So if you can do that, and you can generate large currents of a large length scale, and you can make the whole thing insensitive to the application of a magnetic field, then you have a material that potentially can generate a large current, and a large current means a large magnetic field.
So in bulk superconductors specifically, and the other forms of material are long conductors, which have their own advantages for things like reducing losses in transmission, but have huge processing issues, and thin films, which are good for making small structures but over large areas for the electronics industry. So bulk superconductors are, as I said at the beginning, localized but large entities. And the way we generate field is very straightforward. We induce an eddy current, and an eddy current flows in a circle, and the magnetic moment of the eddy current is simply the product of the size of the current by the area that it defines. And if you have a bulk material that looks like a hockey puck, and these materials are often described in that way, you have nested current loops, you simply integrate the magnetic moment over the area of the sample to get the net magnetic moment. So it's a summation of all these individual current loops. So clearly, if you go to a larger diameter loop, you get a bigger magnetic moment and a bigger magnetic field. So that's what we want to do. And note that the magnetization therefore increases as you make your sample bigger. If you take a permanent magnet, where the magnetization is net magnetic moment per unit volume, you double the volume, you double the magnetic moment. So magnetization, all but for very small geometry samples, is independent of sample volume for a permanent magnet. So there's no gain in going to a bigger sample, whereas in a superconductor, the bigger you make it, the bigger the field it should generate. So the whole message is big samples carrying larger currents give you big magnetic fields, and that's where we're going. Okay, so to say something about magnetic irreversibility, so this is the equivalent of the BH curve or the MH curve for permanent magnets. So we apply a magnetic field to our superconductor, and it's diamagnetic, so we induce eddy currents on the surface of the superconductor that resist the application of the field. And if there are no demag effects, and there always are, but if there aren't, if we were to make these units right, so we'd have to multiply this by mu naught, this angle would be 45 degrees. So the superconductor would generate an equal and opposite magnetic field. So I'm just representing that here. Here's the applied field. Here's the equivalent of the field generated by the superconductor, or its magnetization. They're equal and opposite, so if we add them in the body of the superconductor, they cancel to zero. And since Flux lines have a beginning and an end, that means they must be expelled from the superconductor. So this is an example of a Meissner state where the flux is being excluded from the superconductor because currents are flowing on the surface. If we then continue increasing the field, you can see the magnetic pressure here is greater than the magnetic pressure here. Eventually, flux is forced into the superconductor, and that occurs at some well-defined field here. And then eventually, flux penetrates right to the center of the superconductor, and that corresponds roughly to the minimum in the magnetization, the most diamagnetic character. If we go to higher and higher fields, we force more and more flux in there. The applied field is in the opposite direction from magnetization, so it becomes less negative, and it kind of decays away. And this actually extends right up to very high field. So for high temperature superconductors, they retain their superconductivity up to hundreds of Tesla. And when we decrease the applied field, well actually I should say we get to a point where, as we go to higher and higher field, the Lorentz force, the thing that makes the flux lines move, gets bigger and bigger and bigger, and at some point the Lorentz force exceeds the pinning force and our flux lines start to move. And at that point it becomes reversible, so there's no hysteresis, but then when we decrease the temperature, we turn to minimum Lorentz force, we turn that pinning back on, and now flux, having got into the sample, can't get out. So we can decrease the field right to zero. Essentially all we've done is flip the currents, they're flowing the other way. So in the zero applied field state, our superconductor is carrying current everywhere, and hopefully it's all in the same direction. If we look at the width of the hysteresis, that's proportional to the critical current density, or the current that our sample can carry. So we want this hysteresis to be as wide as possible, and the stronger the pinning, the wider the hysteresis, and the bigger the field. So that's how we interpret the MH curve, or the magnetization curve of the superconductor. The field at which we get this pinch-off, where the hysteresis disappears, is called the irreversibility field. And essentially we need to be working below the irreversibility field at a given temperature if we want to maximize the properties of our sample. And as we go to lower temperature, this point moves to the right. So this plot here shows how irreversibility field, this pinch-off point, varies with temperature. And you can see we can define a line, and we have the different high-temperature superconductors here, the bismuth-based materials, which have a TC of between about 90 Kelvin and 110 Kelvin, have a fairly low irreversibility line, whereas the rare earth-bearing cuprates have got this high irreversibility line. HC2 represents the limit above which the material is not superconducting. It's a reduced temperature scale, which is a slight inconvenience, but if we read up and across at 77 Kelvin, for the bismuth-based materials, we see we get a very small magnetic field. There's no way at 77 Kelvin we can use the bismuth-based materials to generate large fields, whereas at YBCO, we read up and across, we get a field of about 5 Tesla. And that's significantly bigger than anything we can do with permanent magnets. So that tells us that the rare earth-bearing cuprates have got the most potential for applying these materials at high field. Thallium-based materials have potential, but it's generally unrealized. They're toxic and they're difficult to process. And we have a colleague who had his lab closed when something went wrong. So it's perceived to be probably more trouble than it's worth, and I've never seen properties of bulk thallium materials. So we're kind of stuck with the rare earth-bearing copper oxides. Ironically, the first superconductor to be discovered with a TC above 77 Kelvin was YBCO, and it's still the best. So we thought this would be the beginning. It may actually end up being the end. Okay, so we take rare earth-bearing copper oxides, and we look at their microstructure. And I actually personally took this micrograph in 1987. It was one of the first IPCO samples I made when I worked at Plessy. And you can see that we've got this very granular structure. And the problem with YBCO, I said at the beginning, we want large currents on large length scales. These grain boundaries don't conduct current very well, they're insulating. So we don't get currents flowing over large length scales, we get very localized intragranular currents, and they give us very small trapped fields. So multigrain YBCO is no good. So our options are limited. If we want to generate large magnetic fields at 77 Kelvin, we need large grain boundary-free rare earth-bearing copper oxide. And fortunately, there are melt processing techniques available to enable us to eliminate those grain boundaries. We make single grain material. And here are the candidate materials. YBCO, which is straightforward to process. These other rare earth bearing copper oxides, samarium and neodymium, have got other features, in other words, other higher TCs, which give you better properties at 77 Kelvin. But you can see samarium dopes on the barium site, and that reduces TC. And that complicates processing, and I'll mention that a bit later. But YBCO has got the greatest potential for short-term high-field applications. As I said, the first material is still the one that's got greatest potential. Okay, so how do you make rare earth-bearing copper oxide? Well, this is quite neat. I went to a lecture at Cambridge, a materials lecture, second-year materials lecture on teach yourself phase diagrams, and the lecturer said there's no known use for a peritectic reaction, practically. These materials are based on a peritectic reaction, so this is probably the only useful peritectic reaction. Some say there is a peritectic reaction in steel making that's useful, but whether that's true or not, I don't know. So what's a peritectic reaction? Well, it's when one solid decomposes to form another solid and a liquid phase. So in this case, we have the superconducting phase, the rare earth 1 barium 2 copper 3 phase, known as the 1,2,3 phase, decomposes to form a second solid, the rare earth 2 barium 1 copper 1, which is the 2,1,1 phase, and the balance of mass gives us a barium cuprate liquid. So we then take a structurally compatible seed with a high melting point, we put that on the molten mix, and then we cool slowly back through the solidification temperature, excuse me, and that gives a single grain that we can nucleate in a controlled way, heterogeneously, and grow. So a suitable seed for YBCO is often samarium barium copper oxide. It's got a higher decomposition temperature, and that means we can partially melt a YBCO without decomposing the seed. It's slightly more complicated than that, but here's a schematic illustration of what happens. Here's our sample at high temperature, and we've added a seed here. We've got a temperature gradient, hot end, cold end. We're cooling the whole thing down. So the growth front is at this point, so we've grown from right to left. And what happens at the growth front is that we've got this 2-on-1 phase indicated by these circles, and that's being dissolved at the growth front to liberate yttrium, because we need yttrium for our barium copper oxide mixture, liquid, to grow our 1,2,3 phase, which is superconducting. So two things are qualitatively happening. One is we're dissolving the 2-on-1 phase of the growth interface, and the second thing is that we're growing at a certain rate. If notionally we're growing at a significantly greater rate than we're dissolving, then we don't have time to dissolve all the 2-on-1, and some of the 2-on-1 gets left behind. And you can see in the solidified bit of the sample, we've got smaller 2-on-1 particles because they've been partially dissolved, and then inclusions, discrete inclusions in the continuous 1,2,3 superconducting phase matrix. There are some nice tricks you can do, and that is, if you're leaving yttrium behind, eventually you're going to run out of ingredients, so your grains are going to stop growing. Also, you've got a lot of liquid around, so the liquid spills out. That makes a real mess of the furnace. I think we've got through about 4 or 5 furnaces where we've had excess liquids produced at high temperature. But if you actually enrich your starting composition with some of the solid phase that you're producing pyrotechnically, then you've got more solid there to grow, and you've got more solid to keep your liquid in one place. We add a bit of platinum for other reasons, so we enrich our starting composition with up to 40 molar % excess of this solid phase. You can use yttria and you can use other things as well, but basically this gives you fairly good results. And if you get it right, this is the kind of sample you produce. So this is 3 centimeters diameter. Here's our seed crystal. We see the 4 facets. That tells you of crystallographic integrity. They're not grain boundaries. And even though I've seen many thousands of these samples now, I'm still amazed by just actually their beauty. And maybe I should have brought one with me, but they're just spectacularly attractive. It has been speculated they make a good contribution to the jewellery industry, which is kind of an insult given the effort you put into making them, but they really are spectacular. If you were to make a single crystal of YBCO, I think our colleague made a single crystal 2 millimeters diameter after a 6-week growth process. So you can't make them in a single crystal form, but you can make them in melt process form. And if you look at the microstructure, you see all these 2-1-1 inclusions in there, and then there's a continuous percolation path all the way through, and we can speculate that these 2-on-1 particles might become magnetic flux. So we could say we're killing 2 birds with 1 stone. We're growing the material, and if we can make these micron-sized 2-on-1 particles even finer, they would form effective flux pinning sites. Well, that's what we thought. And we thought that because if you look at how critical current density varies with the number of these particles you have in your sample, you see that JC increases roughly linearly. So that suggests that 2-on-1 is forming a very effective pinning site. However, it necessarily doesn't form the optimum flux pinning site. And I've got to say, for a decade, we were obsessed with making 2-on-1 particles smaller and smaller and smaller to get higher and higher JCs. And we'd actually missed the point, and part of this talk will be to explain how we missed the point. Okay, so if we look at the different rare earth barium copper oxide materials available, the ones that are shaded light blue are the light rare earth elements, and they tend to give you better properties. So they give you higher transition temperatures, and they give you higher JCs, and they give you higher irreversibility fields. So you'd like to make lanthanum, neodymium, samarium, europium, or gadolinium barium copper oxide. If you look at yttrium, you get less good properties. However, the question is, you can see yttrium with any one of these, but what do you see these compositions with? It's not obvious. And there isn't an obvious seed available. One way you could do it is a hot seeding process, and the Japanese are very good at hot seeding. One problem with these light rare earth barium copper oxides is that you have to process in reduced oxygen atmosphere, because if you don't do that, you get the substitution of the rare earth element on the barium side, and TC comes down and the properties become inferior. So you've got processing challenges, and you've got a seeding challenge. So what do we need from the seed? Well, obviously it's got to be a high melting temperature, because if it isn't, it's going to melt before our parent sample does. It's got to have a good lattice match, so we get a good crystallographic phase. And it's got to be stable. There's no point if the seed reacts with the material we're trying to grow. So here's just a reminder of these decomposition temperatures. You can see that these are very high compared to YBCO. And the way we measure it is from a 45-degree tangent to the DTA signal. So some people measure it at the minimum, others from the top. As long as you're consistent, it's only a relative measurement. And as a result, neodymium barium copper oxide and samarium barium copper oxide are used widely to seed YBCO. So the Japanese use a hot seeding technique, and I've seen the lab at which this happens. It's pretty spectacular, I have to say. So you take your material, you heat it up to a decomposition temperature, you allow it to perotectically decompose, you cool it quickly to just above the perotectic temperature, you open the furnace door, and you put your seed on the sample. And the one I saw, it was a tube furnace. This is 1,000 degrees C, and the seed was 1 millimetre by 1 millimetre. It was on the end of a long rod, and you have to push this into the middle of the sample, into the middle of the furnace, and tip it onto the top of the partially molten sample. Quickly take your rod out, reseed this, and hope you don't interrupt the processing atmosphere. It was unbelievable. But when it works, the samples are extraordinarily good. You could argue it's not commercially compatible, but you can't dispute the processing sample you get. Quite often, well, the Japanese quite rightly tend to publish the successes, but I was told it only works 1 in 20 times. They've developed a different technique where you seed from above now, but it's still a very difficult process to control. So in terms of hot seeding, you obviously require a specially designed furnace. Multiseeding is difficult, so if you want to grow anything other than a cylindrical sample, you've got a problem. Processing in a controlled atmosphere is difficult. However, the Japanese, as I've said, have done this successfully, but significantly, non-Japanese laboratories haven't been able to do it. And that includes my lab. We tried and tried and gave up, and it's not economically viable. But it gives you hope that you can develop a process that works. So our challenge was to develop a more practical process. And the way we did it was to have 3 different influences in the processing. So the first was to develop a new seed, which we could use at room temperature. The second was, it's pretty obvious in retrospect, but if you add excess barium to the composition, it inhibits the doping of the rare earth element off the barium site, and you don't have to worry about a processing atmosphere. I can't believe how simple this solution was after we'd spent months and months trying to work out what to do. And the third thing is to introduce better pinning centres, much better than the 2-on-1 phase. And if you do that, you can use a standard melt process in a normal furnace, you add the seed at room temperature, and you can grow single grains. So you get a very simplified process with good properties. Okay, so let me tell you about the development of the generic seed. I have to say this was done by my PhD student, Hua-Shi. She's an SRA, Senior Research Associate in my group. She actually joined my group in 1975 as a technician. So we have a policy where we put technicians on papers if they contribute to their content, quite rightly. And after she published 60 papers, she decided she might do a PhD, which she did. She then became a research assistant, then a research associate, now an SRA. It's quite a story, and she's very modest, so it's a good job she's not here. She wouldn't like me telling you. But this generic seed crystal was discovered during her PhD. And she tried a number of compositions, but she found if she doped neodymium barium copper oxide with magnesium, you get this large increase, 20 degrees, in decomposition temperature. And it's reproducible, and you can see all the elements you might want to melt process here have this high melting temperature. And I assert that this seed can be used to melt grow any rare earth barium copper oxide. In her viva, she told the external examiner that she was lucky. And that was probably the understatement of the year. It was a carefully designed experiment, and she deserved to find this material. So this is now patented, but it gives us this 15-degree window of processing where we can seed and grow a single grain. If we actually add magnesia, we see that for up to 1 weight%, we get this big increase in decomposition temperature, and then it levels out. So the magnesium is going into the lattice for these small dopants, and here it's existing as a second phase impurity. This was part of Boischi's PhD thesis. So you only need 1 weight% magnesia in neodymium, and you get these very nice seed crystals. The first thing you do is you send them to a different lab, and we did that. In fact, 3 labs have used these single crystal seeds to melt process their own materials. So other properties, lattice matching. So here we've got our magnesium doped seed. At the bottom we've got our neodymium 123. You can see there's a very good lattice match. The peaks are in the same position. In fact, it's less than 0.7%. The way that neodymium barium copper oxide was grown previously was using magnesia, and there's a 20% mismatch. And that gives you very low reproducibility in forming a single grain. But with the high temperature generic seed, we get this very good match between lattice parameters. Okay, this looks at the phase stability of the magnesium doped neodymium barium copper oxide. So we've taken a variety of conditions. So here's straightforward 1, 2, 3 with its low decomposition temperature. If we then add magnesia as a precursor powder, there's some pre-reaction, and immediately the decomposition temperature increases. We then put 1 weight% magnesia in our crystal, we melt process it, and then we look at the DTA of the crystal, and again the temperature is high. And then finally, and most searchingly, we take our magnesium doped neodymium barium copper oxide crystal and we add to it some very corrosive liquid, a liquid that would be formed at high temperature in a melt growth process, and we still see this high decomposition temperature. So this shows you that the seed has got the right structural characteristic, it doesn't react, and it's stable at high temperature. Okay, so what I want to talk about now is how we improve the ability of the material to carry current, how we can improve JC. And we're going to do that by putting in second phase inclusions, so physical obstacles to the motion of flux through our bulk material. And there's a story here, and I've told it a number of times, so I'll tell you, and this is truthful. It all started by adding uranium to YBCO. So there's a lab in the US called, it's at Houston, Roy Weinstein looks after that lab, and he reported, they're into kind of serious science, like putting lots of radioactive stuff in and zapping it with various things, and getting fairly spectacular effects, and having to wait 4 years before you can measure the sample because they're too hot. And he reported if you put fissile uranium in, it's all a bit scary, isn't it? And you irradiate it, then you can get fission fragments that do local damage, and they form very good pinning centres. So I thought, well, we can't really do the fission bit. So what if we get depleted uranium and look for a chemical effect? But at the time I was doing some work with British Nuclear Fuels and Urenco, I thought this might be a way of getting some money out of them. So I used this vague Houston data and said, we're going to put uranium in our samples, and they were very keen to do this. So I remember the phone call, it was along the lines of, well, how much do you want? And I said, well we're going to start with 7 grams of depleted uranium. And they said, well, we've got 7 tons of it. I said, no, 7 grams. Well, what about 700 kilograms? So in the end, we settled for 30 grams. They were most disappointed. But I remember the discussion I had with my postdoc was that I actually said, I can't believe this is going to work, because the Houston study was all about the products of fission and the damage that did, and microscopic damage tracks through the sample. And we had nothing in there that was radioactive. So I said, I just don't believe it will work. And then, so we made this melt process YBCO. We didn't even use a seed crystal, we just used multi-grain. And Harry Babby, who did the work, came to show me this viewful. He said, I can't believe it. He said, see these bright spots, they're uranium, so you get lots of contrast in the SEM. He said, they're tiny. He said, I've done nothing. He said, I just put it in the furnace, I press the button, and this is the distribution. We've spent 10 years trying to get 211 to this size, and we're still 10 times bigger. You know, it's spectacular. So we then decided to work out what this phase was, but typically it's 40 to 50 nanometers in diameter. It's so difficult to identify the phase composition, and it took a long time to do it. But when we did it, what emerged was a new phase. We call it the 2411 phase. Yttrium, barium, yttrium-2, barium-4, copper-1 and something else. And in that case, the something else was the uranium phase. So it's a 2411 where the 1 is uranium. And we then, I guess that took 2 years to identify that phase. We've subsequently found 48 compositions with a whole bunch of different M elements that form single phase material. And from the XRD trace, you can see they're all single phase. So we've got the uranium, the bismuth, the tungsten, the niobium variants. And they're all double perovskite, so you get a slight variation in lattice parameter, but they're all stable, and we can make them all in single phase form. Better than that, we can change the rare earth element. We can go from yttrium to gadolinium to samarium to neodymium and make 2411 phases out of all of them. And again, these are just some of the others: samarium, gadolinium, and yttrium. Different traces are cleaner than others, and we can control the lattice parameter very accurately. So this then was a very promising flux pinning centre, a very novel one. Again, we patented it. Let me just show you the microstructure. So here we've got the zirconium variation of 2411, and you get these tiny second phase inclusions of the order of 10 to 20 nanometers. Remember, 211 is 1 to 10 microns, and the smaller you make these pinning centres, the better. You want them of the order of the coherence length of the superconducting charge carriers, which is round about tens of nanometers. So this looks very good. And the other thing is that you're not using 211 to control the process and control the pinning. If you want fine 211, it means that you don't have high temperatures for a long time, which means you're limited in your processing. If you want to liberate your processing, you have high temperature for a long time, but 211 materials tend to coarsen. So that means you don't get the pinning. So we made the mistake for more than a decade of trying to do too much with one effect. And as soon as you put in this fine second phase material, that liberates you from worrying about the 211 for pinning. So here's a bunch of others. So here's the tantalum variant. Again, these very fine dots are the 211 tantalum-based pinning phase. Ruthenium, again, it's a very nice array of second phase particles. Hafnium, this is along one of the facet lines. Again, these tiny dots are the 211 phase. And I think the tungsten one is the most telling one. Here's a 211 particle, and you can see the tiny dots, smaller than the dot of the laser pointer, are the 211 phase. So that gives you a graphic illustration of how you can engineer pinning sites if you use sensible inclusions rather than try to work for 211. And again, this work's been reproduced by a number of labs, but noticeably in Japan. We've got a colleague at one institution who joked, well, it wasn't really a joke, but they can now make samples better than we can using our additives, which I think might be true, sadly. Okay, so what about the properties of those samples? So we're going to look at yttrium-2411 and gadolinium-2411, and we're going to use a material that's grown in air using the generic seed, so no specialist processing atmosphere. And here are just different materials. So we've got yttrium barium copper oxide, single grains with and without 2411. We've got a gadolinium single grain with 2411. So the point there is we can virtually make anything out of any composition there. And we can just compare JC. Remember, we want JC to be as big as possible. That gives us the biggest possible fields. And if you systematically add more and more 2411, eventually you get too much of a volume fraction, so you don't have the superconducting cross-section to carry the current. But around about 6 to 8% 2411, we get this big increase in JC. So more than a factor of 3 increase at intermediate fields where these materials are more likely to be applied. So about 6 to 8% is the level of enrichment that we're looking for. So we have this at the powder processing stage. And if we now look at how JC, sorry about the axis, something went wrong here. If we look at volume fractions of function of JC, which is comparable to the earlier plot for 211 I showed you, we get a fairly steep slope for the 2411 addition, whereas a 211 it's a much more shallow slope. So that tells you the principles of return give you a lot better JC properties if you use your 2,4,1 phase. Okay, so if we take a single grain, so this is the gadolinium barium copper oxide, we find that silver works best for gadolinium, and if we add the niobium doped 2,4,1 variant, we get this big increase in JC, again at intermediate field. So this is a fairly dramatic improvement. So this is suggesting that around about 2.5 to 3 Tesla, these pinning centers become less effective. So after all that, what trap field do you get? Well, in theory, the bigger the sample, the bigger the trap field. So this is a gadolinium barium copper oxide sample, the one that I've just described. It contains the 2,4,1 phase. It's only 25 millimeters diameter, and we're getting a trap field of more than a Tesla. And the whole point about bulk samples is that if you then levitate a permanent magnet using a bulk sample, that levitation is stable. So the pinning centers will resist motion. So rather than the unstable levitation you get with a bulk permanent magnet, with a superconductor, it's stable. And that's one advantage that superconductors have over conventional materials. But you get this nice inverted beam cone, so we've applied a field, we've removed it, and we've scanned a Hall probe across the surface, and you can see this peak field is getting on to 1 Tesla. If you increase the sample size, it goes up to 1.2 Tesla. That's a nice sharp peak there, and there's potential for applications using the geometry of that beam cone, and I'll come back to it. But again, this is a slightly bigger sample. Okay, so if we started constructing this plot, so it's trap field versus diameter of single grain. The red stars on here are our samples, everything else is other people's. And the other people's samples have all been processed using either hot seeding or reduced optimal partial pressure. And I really like this plot. For undergraduates, I say, whenever you put a plot up like this, be careful where you draw your straight line, because you can draw it anywhere. In my case, it was very convenient to draw it here because all our results are slightly above it. But you could argue there could be a different straight line there. So we're trying to move further and further up here. So we're now looking at different ways of pressing the form of our green body to try and access these very high fields, but using a very practical processing technique. The process we have enables batch processing, so we can make any number of materials. So this is our chamber furnace. It looks pretty untidy, but we can make 20 samples in one go. There's no way you can do this if you're using a tube furnace with a controlled atmosphere. And if you're using multiseeding, hot seeding, I've got absolutely no idea how you tackle this. But we've made 20 samples of gadolinium barium copper oxide. You do get a slight variation in performance of samples around the side, but they're much better than anything we can make with YBCO anyway. So this is the basis of potential commercial application. And we can do things like cold seeding. So here's our single seeded sample, and here we've used a bridge seed, which I'll say a little bit more about later on. And again, it's all possible because we've got this very practical processing method. Okay, well, I mentioned record fields at the beginning, and I showed you this, this view graph. So 17 Tesla is the current world record. We have these nice experiments in my group. We call them Friday afternoon experiments. And anybody can suggest any experiment. It's okay to suggest crazy experiments. And they may be high risk, but we'll give them a go. And if they come to nothing, then it's just a Friday afternoon with lots. So we were kind of discussing this Japanese result. And we said, we keep saying we make these good flux pinning samples. We ought to be able to do better than this. So there's a guy called Eric Hellstrom at the National Highfield Magnet Facility in Florida, I know very well. So actually over a beer we decided that we'd have a go at this. So our latest Friday afternoon experiment was to try to beat this field. So the first attempt, we trapped 3 Tesla. And we trapped 3 Tesla because there was lots of flux jumps at very high field, and that gives you lots of heat. And that means that bits of your sample go normal, so a current has to go round, there are big forces, and therefore you can destroy your sample, which we did very effectively. But then we designed a way of eliminating that heat leak by putting in a high conductivity material through the centre of our sample. And we went back just before Christmas and repeated it. So our 3 Tesla field, so the red dots were our sample, this is the sample we used, is now up to 11 Tesla at 30 Kelvin. And this is a reinforced sample, stainless steel reinforced sample. Here's our silver heat leak, and here's our bulk sample. And this particular sample is 33% smaller than that used by the Japanese. So the energy density is probably a record energy density already. But this sample failed mechanically, and we've already worked out how we can reinforce it. And we're going to repeat the experiment in April. And as John Durrell's my postdoc, who's the world's biggest optimist, and he reckons if you extrapolate these skirts here, spookily enough, you get to 17.8 Tesla. And this is his view for rather than mine. But the whole point is, our temperature is slightly higher than Murakami's, is, and our sample's a lot smaller. So if it gets anywhere close to 18 Tesla, it will be a record field and a record energy density by some way. Okay, so I mentioned earlier multiseeding. Well, this was an experiment we did a couple of years ago, and it's all right using a single seed, but you may want a sample of conformal geometry. You might want to put it in a motor, or you might want it to be for a shim of a magnet. And a cylinder may not be the most appropriate way. So we took a piece of melt process material, and we cut out the middle, which gives us two legs, and we used each leg as a seed. So this is a doubly seeded material. So here's our doubly seeded with the seed removed. So there's a grain boundary down the middle. And we can increase the separation of the two legs. So you can see the separation is getting further and further apart. We can go to more than one nucleation site. So here we've got 5 nucleation sites. When we remove the grain with the seed, we see this site. You can see the facet lines here as well. So the question is, what are the properties of these grain boundaries? Because we know rare earth barium peroxide, the grain boundaries are not very kind. And common wisdom was that it was this separation critically determined whether the grain boundary was any good. So if you measure trapped fields of these different materials with small separations, bigger separations, and a large number of seeds, you see you get roughly the same profile. So that tells you the length scale of the current flow is the same. So these grain boundaries don't interrupt the flow of current. So therefore, it's not the separation that's important, it's the orientation. And if you get the orientation right, then multi-seeding should be very possible. Obviously, if you don't have a bridge-shaped seed, it's difficult to control the orientation. And we're doing some experiments now where we rotate one of these samples through 45 degrees. So when the grain boundary is impinged, they do so at an angle. And if there's any impurities, they're pushed away rather than trapped at the grain boundary. And we just saw these samples last week, and already the results look extremely good. So maybe we've got a way of engineering these grain boundaries. Okay, so I'll just finish off now by talking about applications of bulk superconductors, and there are a number. So the first obvious application is magnetic variance in maglev. This is a Shanghai maglev. It's a bit of a cheat really, because there isn't a superconductor in sight in the Shanghai maglev. And here it's levitated. This is the first levitated capsule using bulk materials. It's done by the Southwest Jiangtong group in China. This test track's only 10 meters long, but they say it's traveled over 500 kilometers and carried 40,000 passengers. You can levitate getting on for a ton. It's pretty impressive. I've actually been on it. Made me feel sick. The way you would do it practically is you have a cryostat. You have 4 of these at the end of each carriage, and each one of these cryostats have got bulk materials in. It's self-contained, and it can support about a ton. And if this video works, I might even be able to show you. Okay, so there you go. It's levitating above the track, the magnetic track, and it's bouncing off there until it doesn't want to change its magnetic field. It's very stable. There's no resistance to horizontal motion because the field isn't changing. There's a well-defined gap, and there's no external active control required. It's completely passive. Okay. So, and they say that will levitate a ton. He's impressed. Okay, and you can see it's stable. It won't fall off the track. So there are so many benefits potentially, provided you can keep the material cool, using these materials in levitation. There's things like flywheel energy storage, which I won't dwell on, but we've just supplied 50 samples to Boeing so they can make flywheel. That levitates. This is the flywheel, I won't go into detail. But the advantage is that if you have a mechanical bearing, you lose your energy very quickly. If you have a superconducting bearing, then you retain your energy. But the advantage is that you can get the power out. Battery, you can keep the energy, but you can't get the power out. For a flywheel that uses superconducting bearing, you can get the energy in and the power out. Okay. Motors and generators are probably an obvious one. You can potentially throw away your iron and use superconductors with bigger fields. And just a couple of things I want to mention in the end. Here's the track field of one of our samples. You can see this very sharp peak. You can use this for drug delivery. So if you can make your drugs magnetic, you can kind of direct them through the human body using this peak field here, which is very precise control. You deliver the drug to where you want it released. It enables treatment where surgery is difficult, reduces side effects, and you can use smaller doses. That's from Japan. And here are the first MRI images using a bulk superconducting magnet. It's slightly lower than 77 Kelvin, but a bulk magnet is providing the field, and you can see, in this case, it's the embryo of a mouse, but you can get good detail. It's certainly good enough to get basic measurements. Okay, and finally, I quite like this. Novel applications. In Japan, obviously they have problems with earthquakes, so you can stabilize items against those earthquakes. So the green hooks here are YBCO on a stage. There should be a video here, but it doesn't work. It's not streamed properly. But this will show that this top plate is absolutely static. So you couldn't use it to support buildings, but if you had a sensitive piece of equipment, you could protect it from a seismic shock. Okay, so let me conclude. So I hope I've convinced you that bulk, rare earth, barium peroxide materials have got enormous potential for high field applications. They're very exciting. You have to be able to control flux pinning, but if you do that, you can improve the track field significantly by adding the right inclusions, in this case, 2411 phase. Gadolinium barium peroxide is a light rare earth barium cuprate. And the seed crystal helps you fabricate that, which gives you access to much higher fields. Batch processing is possible if you design your top-seeded melt growth process properly, and there are lots of exciting and emerging applications. So sorry it was a bit rushed at the end, but thank you for your attention.
I do realise that some people have teaching obligations at 2 o'clock, and if you have to leave, that's absolutely fine.
Everybody leaves.
So, any questions? Mike.
On the types of material or defects that you can use for flux pinning in these materials?
I think there are limits. I think the problem we have with our subject is that people get set in their ways, and they don't look where those limits might be. So different groups have looked at novel ways of making flux pinning sites on the nanoscale, from machining 2 on 1 for 3 days, to adding new materials, to looking at things like dislocations, some kind of lattice inconsistency. The consensus seems to be that there aren't limitations if you avoid magnetic species. If you put magnetic species in there, they seem to interfere with the superconductivity. But apart from that, there are no well-defined limitations. The problem with these materials is that it is a melt process, and that really is your rate-determining step. You have to control the melt process, and anything you get as a result of that is a bit of a bonus, to be honest. So when a material comes along that's stable, doesn't coarsen, doesn't react with the material, you can engineer the lattice parameter. Probably I would say this, but that's probably about as good as it gets.
How well are the details behind the seeding process actually known, do you think, on a microscopic level or a thermal level?
Yeah, that's a good question. So to some degree it is a black art. I mean, the principles of homogeneous rather than heterogeneous critical radii are known, so we know why ponds freeze at the end rather than the middle. And those principles do apply. With rare earth barium cuprates, the key thing is that depending on which crystallographic direction you grow in, you get a different growth rate. So it's orthorhombic. A is roughly equal to B, the growth rates are about the same, which is why we get a square grain. But the C-axis, which grows down through the material, is a relatively slow growth direction. So what happens with the seed is that all directions other than A or B grow fairly slowly. So A or B dominate, So whatever geometry seed you use, you always end up with a square planar seed at the centre. And we've done many experiments like partially growing and quenching. So we've done studies of growth rate versus temperature, growth rate versus undercooling, growth rate versus composition. And you can look at the consequence of that. Because you've got all these small particles, you've got a growth front, it tends to push these particles ahead of it. And the particles will build up and build up and build up, and then you'll trap a whole bunch of them in one go, and then you'll start again. So quite often you can see banding structure, and that tells you again about the nucleation process. But some groups have looked at different side seeds, and to start with, it was thought that a large seed will give you a much better homogeneous sample, because you can get uniform nucleation all over the seed. Well, in theory you can, but practically you can't. The bigger the seed, the bigger the chance for temperature variation, and the bigger the chance for secondary grain formation. So again, that distracts us for another 6 months. So I'm conscious that I've been distracted for longer in my life than the time I've been working on superconductors. But again, it's a good question, and so we know enough, but we don't know everything about the seeding process.
Well, just from an applications point of view, are these materials machinable?
Yeah, another good question. They're brittle, so they're not. They are machinable, but you've got to know what you're doing. So typically, machining these materials takes a long time. You want to avoid lubricants that are water-based, and you want to avoid generating excessive heat, because when you make the materials, you have to oxygenate, and temperatures of 100 degrees upwards will cause the material to lose their oxygenation. So you do things like slow machine using diamond blades. You can trepan, that's okay. Laser cutting is a good way, but you've got to have a conducting, spark cutting is a good way, but you have to have a conducting sample to do that. So over the years, cutting and shaping is not a problem for us, but if we had to do 1,000 of these a week, then it probably would be. But to do scientific experiments and produce the geometries we want, shaping and cutting is not a problem.
But from an application, an ultimate end user application point of view, is it something that can be productionised, or is that an issue?
You'd have to productionise it. If you want to make so for Boeing, with the 58 samples we provided, they wanted hexagons, so we made discs and machined them. The way to do it would be to have a hexagonal die, and just to melt process in the form of hexagons, and then just to polish the edges. That would be the way to do it. To put it into context, each one of these samples, I think, at research costs is about £400. I think to apply them, you've probably got to get that down to about £100. I can see how you could get it down to about 170, but I can't see how you could get it down to around about £100. But I think the post-processing, the cutting, the shaping, the polishing, is a big part of that. So if you get it right at the beginning, and predicting your final geometry from your initial sample size, given you've got this melting and reforming, is another black art to some degree. But so there's still a lot of work to be done there.